Okay, so let's start here. I want to share my slides here. Okay, I guess that's the right one. Okay, so now I'm sharing. Okay, so let's start today. In this chapter today, we will focus on the physical layer technologies used in wireless digital communications. So if you are working from the electronic communications book, you're going to find that covered in chapter 8. If you're using the modern electronic communication, you're going to find the topic covered in chapter 10. Um, so we said that we're going to be talking about wireless digital communication. The term wireless is used today to describe any kind of telecommunications technology that use radio waves rather than cables to carry the signal. So wired technologies can be divided into three main groups: fixed wireless, and this will have both transmit and receive units are at fixed locations. And an example for that is the LANs, which is the wireless local area network. Another one wireless technology is mobile wireless, and here you're going to find that the transmit and the receive units are going to be moving, and you can find an example like that. The cellular, your cell phones, for example, is an example of a mobile wireless. So for the fixed wireless, you're going to find your transmit and receive units are fixed at fixed locations. For the mobile wireless, they are moving. And then we have infrared wireless, where the transmit and the receive units are infrared light sources and detectors to provide the different kind of communication links. For example of that, you're going to find that in a building to building communications link. So this is just an overview of the different types of wireless technology. Um, the transmission of digital data via frequency modulation or phase modulation offers some of the same advantages over amplitude modulation that can happen in the same analog system. So today we're going to be focusing on digital modulation. So digital modulation involves modifying the amplitude or the frequency or the phase characteristics of a carrier corresponding with the data stream that is representing the ones and zeros. So when we're talking about digital, we always think about our data is a pulse of ones and zeros. Now that data is going to be modified somehow or modulated either by amplitude or frequency or phase to get transmitted wires over to the receiver. The simplest digital modulation schemes change the carrier state with each bit of data. So for example, here we have three different types of digital modulation. One is called the amplitude shift keying, frequency shift keying, and phase shift keying. So we're gonna go over each one of them and know how does it work, what's the main function, main advantages of each. So for example, for the amplitude shift keying, well, the term keying is a holdover from the Morse code era. If you remember, the Morse code transmissions was represented in putting some dots and dashes. That was the first like type of digital communications in the early days. And the Morse code is not really a true binary code of a 1 and a 0 because it not only includes the marks and spaces, but also differentiates between the duration of each condition to give you the different kinds of letters and numbers and all of these things that need to be coded. So here in the amplitude shift keying, what is really happening here, as you can see in the figure, so the most elementary form of transmitting highs and lows is simply to key a transmitter's carrier on and off. So you can see here in the figure that the carrier is conveying intelligence by simply turning it on and off according to a prearranged code. And this type of transmission, what we called a continuous wave. Because this wave is periodically interrupted, we can call it an interrupted continuous wave, ICW, instead of just CW. So here for your, let me just grab my pen here. Pen, and let me just change the color. So we are noticing here, this is your data, the ones and zeros, okay? We are modulating that using an amplitude shift keying. So with the ones, I'm having my carrier. With the zero, I'm just cutting it off. It's like a switch that has on and off. We know that if you notice here on this signal, you're gonna find that the waveform, the sides of this waveform are very steep. So it's just changing from zero right away to a certain value here to the maximum value. So it's like kind of sharp. And this sharp edge requires a lot of harmonic contents. If you remember that, how to design or how to create a square wavefront from sinusoidal signals, we said that we need to use a lot of harmonic signals combined together in order to get this sharp edges here. So the more sharp edge or ideal edge you want, the more harmonics you need to get included. And that means that you need to require a very wide bandwidth so that you can avoid any kind of interference between adjacent channels. So this is one of the like the cons that we need to overcome. And usually this is overcome by using this type of a filter. So what this filter does is it will make the transitions here a little bit, and instead of having it very sharp edge, it's just going to make it a little bit smooth so that you don't need to include a lot of harmonics, and therefore you don't need to have a very wide bandwidth. So here in this circuit here, this filter, it's working in the way that your inductor here will slow down the rise time. So this is your rise time. It will slow down the rise time. So instead of having an instant rise time like that, that is very, very small, close to zero, I'm gonna slow it down a little bit using the inductor L3. And the capacitor C2 will slow down your decay. So instead of going sharply from 1 to 0 or from maximum to minimum, it's going to slow down the decay. And the main advantage of doing that, or the reason why we're doing that, is to avoid requiring a very wide bandwidth, because with the sharp edges I need a lot of harmonics, which means that I need my carrier frequency and all the harmonics, like double, triple, 5 times the frequency and so on. And that's what we mean by the higher harmonics. It means that you need to increase the bandwidth of your channel. Okay. So that is for the amplitude shift keying. Now let's move on to the frequency shift keying. So frequency shift keying is a form of frequency modulation in which the modulated wave shifts will shift your output between two predetermined frequencies. And usually those two frequencies, we call them the mark and the space frequencies. So in another instance, like when we're talking about the mark and the space, a logic 1 is usually termed as a mark, and a logic 0 is termed as a space. We're going to notice here that for the mark condition, it will cause your carrier frequency to increase by 42.5 hertz. We're talking here about the narrow band. And for the space, it will result in a decrease by 42.5 hertz. So it means that your transmitted frequency is constantly changing by 45, which is 85 hertz. Okay. So you're having this is your carrier frequency. You're increasing sometimes by 42.5. You're decreasing by 42.5. So the whole band is just going to be 85 hertz. So the 85 hertz, as I said, this shift is the standard for using a narrow band frequency shift keying, while 850 hertz will be used for a wide band shift keying. And this is just a figure here of your frequency shift keying transmitter. Okay, so here you're gonna have your ones are always represented with mark, your zeros represented with what we call a space condition. So it means that whenever I have the one, I will go above my FC with 42.5 kilohertz. Of course, if I'm in the narrow band, whenever I see a zero, I will go below my FC with 42.5. So it means that here I'm going to have more narrow bandwidth together because this is higher frequency. And here in the space, you're going to find it's a little bit wider. So it's going to be here wide because it is lower frequency. And that's how you are modulating your data here over the intelligence. So it is related to the frequency and a certain increase and decrease to that particular frequency. Now the third type is the most common type that has been used is what we call the phase shift keying, and that is the third type of data modulation, and it's one of the most efficient ones. It provides a low probability of error, and that's the main advantage of it, and we're going to see in a minute. In the PSK system, you're going to find that the transmitted binary data will cause the phase of the sine wave carrier to shift by a defined amount. And we're going to see that in a minute. So the modulating signal may cause the carrier, for example, to shift to one or more possible phases. So if we're having only two phases, it's going to shift between 0 and 180 degree. If we have 4, so it's going to be like 90 degree apart, and so on. So here, let me show. This will be your output of the phase shift keying. As you see here, the sine wave carrier to the shift will be defined by this amount here, where your M is going to be the number of allowable states. So if I'm using a binary, for example, shift keying, then the number of states are 2. N is equal to the number of data bits needed, and we know that the relationship between M and 2, N and M, are that the number of bits here, M is equal to 2 to the power of N. So the possible allowable states will equal to 2 to the number of bits. And your WC here is your carrier frequency. And we know that WC is equal to 2 pi FC. Okay. So we're going to notice here in the phase shift keying, for example, if I have such a data like this, what's going to happen is that when it's equal to 1, I will have my carrier signal just in phase, like with 0 phase shift. And when it's 0, I will have it to 180 degree. So it's going to be flipped. Okay, so it's going to be flipped 180 degree. And then you go back to the 1 is going to be in phase with the original with the original carrier signal, and when it's equal to 0, I phase shift it by 180 degree. That's, for example, like when we're talking about, for example, the binary phase shift keying. So there are basically in the phase shift keying, there's a lot of types, but there's the most 3 common types. One's called the binary phase shift keying. And in that binary phase shift keying, the number of allowable phase states is going to be 2, which is going to be the 0 degree and 180 degree. So these are the phase shifts of your carrier. So you're going to have your carrier signal is just in phase, or you're going to have it 180 degree phase shifted from the original. We have also quadrator phase shift keying, QPSK. This one you're going to have 4 allowed states, and therefore you need 2 bits to produce that. Also, anything that's going to be greater than 4, we call it M-array. Okay, M-array system. So this one is an 8 PSK system with 8 allowable phase states. So you're doing 8 like 0 degree, and you're doing others all the way phase shifting different 8 possibilities. And usually the output signal is called constellation in this case. So the output signals that you're going to have, usually we call them constellation. So for the binary phase shift keying, we just I just explained that in a minute. The carrier will have 2 phase shifts, which is 0 and 100 degree. So assuming that this is my binary input, my first one here, if you assume this is your binary input here, you're going to find out that sine omega CT provides the logical 1, and that minus sine omega CT Victor provides the logical 0. So the binary phase shift keying signal doesn't require that the frequency of the carrier to be shifted. So we're not shifting the carrier frequency. The carrier frequency is the same, but what I'm doing, the carrier is directly phase modulated, means that the phase of the carrier is shifted by the incoming binary data. So all of them are at the same frequency here. You're going to say that they are all the same width, but it's how it is shifted according to the original. So if I have my original signals like this, so this is my original carrier, okay? This is my original carrier. You're going to notice that when it's equal to 1, it is in phase, like it is the same. When it becomes a 0, you do a 100 minus, so you're doing like a 180 degrees. So you're just flipping it. If you think about it, just you're flipping it. When it's 1 again, it's just in phase, okay? It's just in phase. And when it's 0, you are flipping the original signal. Okay, I'm just not doing it good enough, so it should be like that. Okay, so that is for the binary phase shift keying. This is a transmitter and or a modulator and a demodulator generation for the binary phase shift keying. So a block diagram here is showing a simple way to generate a binary phase shift key signal. You're going to find out that the carrier frequency here, sine omega CT, is phase shifted 180 degree by putting it through an inverting amplifier. So you are inverting this, and instead of positive sine omega CT, it's going to be minus sine omega CT. The positive and negative values, so I'm going to take, this is the positive value, this is the negative value, and I'm going to pass both of them, are going to be fed to what we call a selector circuit. And this selector circuit is driven by the binary data. Okay, so if the bit is 1, then your output, so if your bit is equal to 1 here, then you're going to find out that your output is sine omega ct. If the binary bit input that you're feeding the selector with is a 0, then you're going to find out that your output is minus sine omega ct. This one is sine omega ct. The actual devices selected for performing this operation will depend on what is your binary input data rate and the transmit carrier frequency. How much is that? Based on these two, they build up the selector that you see here. So that is how we generate a binary phase shift keying by using a carrier frequency of sine omega ct. So I inverted it, then I have the original one, I have the inverted one through a selector, and the selector is like a multiplexer to choose which one of them based on your binary data that is coming in here. So if you think of this like a multiplexer that has two inputs, one is just sine omega ct, the other one is minus sine omega ct, and based on your binary input data, okay, if it's 1, your switch is going to be here, and that's what you're going to see at the output. If it's equal to 0, then your switch is going to go to the other way around, and then you're going to see the signal phase shifted by 180 degrees. Also, a binary phase shift keying receiver detects the phase shift in the received signal. Here, if we take a look, so this one is how to generate the binary phase shift keying. Now at the receiver side, I'm receiving the binary shift, the BPSK signal. It's fed into the mixer circuit. So we feed that signal into the mixer circuit. The other input of the mixer circuit, so one of them is gonna, so the mixer circuit here has two inputs. One of the inputs is gonna be your binary phase shift keying input. Your other input to the mixer is gonna be driven by a reference oscillator that is synchronized to the carrier frequency. So it has to be at the frequency of sine omega ct. And this is, we usually call this the coherent carrier recovery, because the recovered carrier frequency will be mixed with the binary phase shift keying input signal. And we usually, when we talk about mixer, we always say that mixer means taking these signals together and creating other outputs. Okay, I don't have it here. So for example, by taking these two together, I am going to have a final output of, for example, half. So if I have, for example, if I have my output is equal to 1, I'm going to have my final output is going to be half minus half cosine, okay, 2 omega ct. Okay, that will be my output here at this point. Okay. Now, because I don't want the higher levels of frequency, so if you're looking at this is WC, this is 2WC, so these are considered to be higher frequencies. I'm going to use a low pass filter that's going to cut any frequencies beyond a certain limit here, so that I only have my carrier frequency, and I will eliminate anything that is higher. So you're going to find that this term here will be eliminated, and you're ending up only with this binary output data. Also for the 0, if you do the same thing, you're going to end up having minus half and the same kind of frequency. So your binary output data here is going to be between positive and negative half. And the positive and negative half represent the DC values that correspond to the 1 and 0 binary values. So the positive and negative values can be conditioned for the appropriate input level for the receive digital system. Now let's move on to the quadrator phase shift keying. The quadrator phase shift keying, we call it constellation. It provides 4 vectors for representing the binary data. Of course, when we're talking about 4 vectors here, we're going to notice that they're going to be saving by transmitting data this way, saving in terms of your bandwidth. So in the QPSK transmission, more data are going to be compressed into the same available bandwidth. If we compare that, for example, to the binary shift phase shift keying. So here, this is going to be more efficient bandwidth-wise. You're going to notice here that in the quadrator phase shift system, it uses 2 data channels, and we identify them as I and Q. So one of them we call, it refers like in phase. I refers to in phase. Quadrate means it is like 90-degree phase shift. The signal here, the quadrator phase shift key signal, will require only half the bandwidth that is required by the binary phase shift keying. So if the binary phase shift keying, requires FB as your bandwidth, I'm going to notice that in the quadrator phase shift keying, I only need FB over 2. I need only half of that bandwidth. And we call that, this is like a data bandwidth compression. It's happening in the quadrator phase shift keying. A block diagram here. Let me see if I have it here. Yes. So for this block diagram of a phase shift keying demodulating circuit, you see it here. You're going to find that a carrier recover circuit is going to be used to generate a local clock frequency that is synchronized with the one at the transmitter side. And it will be locked to the input carrier frequency WC. This frequency will be used to drive the phase detector circuits. So these are your phase detector circuits. One of them will take the signal, okay, in phase. The other one will take it 90 degrees out of phase. So that's why I call this is the I path. You're going to find it here, I data, and this is the Q path. So I is referring always to in phase. So this is in phase with the original signal. This is 90 degrees phase shift from the original signal. Usually the base detector, the phase detector here is just like a mixer. Okay, so it behaves as a mixer here. You're mixing between 2 signals. Actually, the sine omega CT that is coming from your carrier recovery and your original signal, or your modulated signal, which is sine omega CT plus phi D. Okay. And the phi D term indicates that the carrier frequency has been shifted in phase, and which is to be expected for phase shift keying data. So the output of the phase detector will then be determined by what we call VBD, which is this relation here. Let me see if I can just erase a little bit this. You can see the equation. Okay, let's go back to my pen. So, as I said, this is coming from your carrier recovery. This is your phase shift keying modulated signal. okay, and they're both going to be passed through the mixer here, and you're going to receive this output. So the output at this point is the VBD, okay, which is half A, the amplitude, cosine 0 plus phi d minus 0.5 A cosine 2 omega CT. Now we notice that we're having low pass filter on both sides here because we want to get rid of this higher harmonic frequency, and we only want to keep this DC value here. So a low pass filter, yes, so a low pass filter will remove this part here and leaving only this DC voltage that is representing the direction of the data vector along the I-axis. The same thing is happening with your Q, but only with a phase shift of 90 degrees. And then you take both of these data here to a signal processing decision circuit to tell you at the end what is your output. You don't need to know what the details here, but you only need to know all the way to I data and Q data. So for example here, if a data value of I and Q, at the end you got the data is equal to 0 and 0, so it means that your original data is located in this part here, okay, somewhere in this part here, and that it is a 45 degrees, your phase shift. And therefore it's easy to calculate the amplitude of that signal by applying this value here, and then you're going to end up with 0.335. Usually, because we all the time we have noise, this is something that we cannot avoid. You're not going to find that your data is just a point. Your data is going to be a cluster of points, okay? So it's going to be, due to the noise, it can make it shift up here, shift there, shift there. So you're going to find that there's a cluster of points. But still, the cluster of points is located in the same data representation of 0 and 0. And that's why we say that it is high immune to the noise, because even if my noise shifted that point, for example, down here, or shifted it to here, I'm still in this particular area. So it will still be demodulated or decoded as a 0, 0. Now there is another type, what we call differential phase shift keying, and it uses the binary phase shift keying vector relationship to generate an output. So the logical 0 and 1 are going to be determined by comparing the phase of two successive data bits. I'm going to compare between both of them, and then in my binary phase shift keying, the plus and minus sign omega CT will represent that 1 and 0. It's going to also be true for this one here in the differential phase shift keying. But the only thing that I'm doing is that I am comparing between two successive data bits. So you're going to notice here that we have an XNOR, okay, and this is like a logic gate. The way it behaves is that if I have two different inputs, my output is going to be 0, and if I have both inputs are the same, so both of them are 0, 0, I'm going to have an output of a 1, or if both of them are 1 and 1, I'm going to have an output of a 1. So I'm taking here delaying by 1 to find a reference, and this is my original data. I compare if it's 1 and 1, for example, they're the same, or 0 and 0, I'm going to have an output here as a 1. It goes through the binary phase shift keying and gives you the positive sign omega CT. If I have them like 1 and 0, so they are different, your output is going to be 0, and then you're going to have a final output of minus sign omega CT. And that is at your differential phase shift keying. So taking a look here at the differential phase shift keying here at your input, this is my reference data. What I will do is I will compare this reference data with my data that's coming in. If they are different, my output is going to be 0. Then I take that as my next reference bit to the current bit. I compare them together. I will find that they are the same. Then you're going to have an output of 1. When they are different, you're going to have an output of a 0. They are different, you're still going to have an output of a 0. Once they become the same, you're going to have an output of a 1. They become the same, you're going to have an output of a 1. The same thing here, you're going to have an output of a 1. So this is the output of this point here, okay, which is going to be a 1s and a 0. Then you pass it through a binary phase shift keying. So every 0 is going to be represented by minus sign omega CT, and every 1 is going to be represented by plus sign omega CT. So every 0 is minus, and every 1 is going to be a positive. Now here at the receiver side, you are receiving this plus and minus sign omega CT. You're also going to use the same thing. You're going to delay it by 1 so that you can compare every current with the previous. The previous signal will be related to your reference, and then so each two successive inputs, you can compare them together and then find your output here. So for example, here at the recovering state, this is your signal here. So this is your minus, this is your positive. So this is now what you received at the receiver side. Okay, now you're going to be using your reference here as minus sign, the same reference we used here. You're going to use that as your reference. And then you're going to check now these two together. If it's both minus, your output is going to be, so both of them are the same, your output recovered data is going to be 1. If they are different signs, your output is going to be 0. Different signs, output is 0. Same signs, output is 1. Different signs, output is 0. Same signs, your output will be 1. So the main advantage of the differential PSK system is that carrier recovery circuitry is not required. So if we take a look here at this one, we don't need to have a carrier recovery circuit that is synchronized with the transmitter. We don't need to do that. And the other, the disadvantage of using the differential PSK is that it requires a really good signal to noise ratio to achieve a bit error rate that is really very close to that quadrator phase shift keying. Now, several special modulation techniques are used. The most popular system to achieve high data rates in limited bandwidth channels, we call it a quadrator amplitude modulation, or QAM. So here in the block diagram that you see, this is a QAM transmitter. You're going to find that the binary data are first fed to a divider data block here. So your binary data is coming here at a frequency of FB. So this is your data. Let's say this is 00111. Okay. So this is a different, like, this is your binary data here. Now you're gonna, this divider here is a clock divider. What it will do, it will decrease your frequency to half. So every other signal, every other clock, I will take the data at this side, and every other clock, I will take the data on that side. So I am here. I'm taking every other data. One will go to the I channel. One will go to the Q channel. So it's producing the two data signals at half the original bit rate. These two level outputs are going to be converted to what we call a 4-level baseband streams. And the result of that will be modulated, amplitude modulated through a local oscillator. So this local oscillator here is going to be having modulated with, directly modulated with the output of the converter, and then I'm going to phase shift that oscillator and then modulate it with the output of the converter. The one that's in phase is going to be your I output. The one that is 90-degree out of phase is going to be your Q output. We have what we call a loopbacks. Many digital modulation systems include a loopback capability. And what we mean by that, the receiver will take the received data and send it back to the transmitter. The data will be compared to the original transmitted data to give you an indication of the system performance, like how much error happened, what did you receive from what you were sending. Calculating the amount of error will give you the like an indication about the system performance. But the bit error can happen both in the original transmission, like before it gets transmitted, you can find an error, and maybe in the loopback, when you're going back, you can have an error. So we cannot really tell where did it really happen, but at least the loopback test is very helpful in like diagnosing the basic system performance. Now we will talk about the spread spectrum techniques. The first spread spectrum techniques here, systems were utilized by the, usually it was first used in the military, because this technique will allow transmission that cannot be jammed, that cannot be detected by others. And later on, it started to be used by other commercial community around. The spread spectrum modulation will transmit a power of 1 watt in 3 different bands. So in the 900 megahertz, in the 2500 megahertz, and in the 5800 megahertz. It is becoming the technology of choice in many wireless applications. These applications are like what you find in your cellular phones, mobile internet, wireless, the LANs, the WLANs, automated data collection systems. Other applications will be used in like remote heart monitoring, in industrial security systems. So as we have seen, regular modulation schemes tend to fully utilize a single band of frequencies. But in this one here, we're going to be in that, I can use different multiple spectrum users can coexist in the same bandwidth if each user is assigned a different spreading code. So I don't have to divide my bandwidth between users, and I don't have to fully give it to one user to use the whole bandwidth, but actually I can have multiple users coexist at the same time using the same bandwidth, but each one with their own spreading code. There are 2 main techniques that exist for spread spectrum. One is called frequency hopping. The other one is called direct sequence. Both forms will use what we call a pseudo noise technique. So let's take a look at the pseudo noise technique first before we talk about the frequency hopping and direct sequence. So the pseudo noise codes are popular in spread spectrum communications because the randomness of the serial output that it creates. The data stream appears to be like a noise-like signal, and instead of just a regular one. So these random data streams are usually used to spread your radio frequency signal so that it appears to be like a noise. So the randomness of the signal that will happen will be due to the fact that the 1 and 0 pattern does not appear to look like it's repeating. So I'm going to be having a random output of 1s and 0s, okay? That will look to me that it's not repeating. So I cannot say that it is something periodic, but actually it is repeating, but after a very long time. That time is really depends on your pseudo noise sequence generating circuit. So if you want to tell how often that pattern is going to repeat, after how many clock cycles, will it be after every 5 clock cycles I will repeat it, after 10, after 100? This will be determined by your generating circuit. So as we said here, your it will require your method here for using a pseudo-noise sequence generating circuit. It will generate a pattern of ones or zeros every clock cycle. And this pattern is not going to be repeated until a long time. And it requires, for designing it, it requires shift registers, feedback paths, and an XOR gate. So a random pattern will be created after you clock your circuit, and it will repeat after a sufficient number of times. And that sufficient number of times, we call it the pseudo sequence length. And the way to calculate that is that it will equal to the number of possibilities according to the number of bits you're using, or the number of shift registers in the circuit minus 1. So for example here, if I want to determine the sequence length of a connected pseudo sequence PN sequence generator, including 3 shift registers. So if I have 3 shift registers, it means that my PN length is going to equal to 2 to the power of 3 minus 1, which is 7. So every 7 cycles, every 7 clock cycles, I will start to repeat my pattern, my random pattern that I created to begin with. Also, if I have 7 shift registers, okay, my PN length will equal 2 to the power of 7, minus 1, and that will equal to 127. So every 127 clock cycles, I will start to repeat my random pattern of ones and zeros. Now, we said that this technique is used, the pseudo-noise code are used to in 2 techniques for spread spectrum. One is called the frequency hopping. So in frequency hopping spread spectrum, the data is going to be transmitted by a carrier that it is switched in frequency in a pseudo-random fashion. So the code, the random code that's going to be generated is the random code for the frequency. So we're going to have a random frequency values that will be created here at your transmitter. The pseudo-random implies a sequence that can be recreated again at the receiver, but has the property of randomness. The time of each carrier block is called the dwell time. So dwell times are usually less than like 10 milliseconds, and this is the time each carrier spends at a specific frequency. So every frequency, I'm going to create a number of random frequencies. Every frequency will exist in a certain time for a block. This block time is what we call the dwell time. So a block diagram here of a frequency hopping system, you're going to find that it needs what we call a programmable frequency synthesizer and hopping sequence generator. So this is going to be generating my frequencies, and I'm going to have a programmable frequency synthesizers that will take the message in and modulate it through a random carrier frequency. So now it's not going to be 1 carrier frequency, it's not going to be 2 carrier frequency, it's going to be a number of frequencies that are randomly created or generated. Also, the receiver must synchronize itself to the transmitter's hopping sequence so that it can be able to recover the original message, and that's going to happen through a synchronization logic circuit that will do that. So what you need to know about the frequency hopping is that the data is transmitted by a carrier that is switched in frequency. So the randomness is not happening in the original data. The randomness is happening in the carrier frequency itself. The other type is what we call the direct sequence spread spectrum, the DSSS. And it's often used in the transmission of digital bits in modern wireless digital systems. The random sequence uses pulses that are shorter than the message bit, and these pulses, we call them chips. So the chips will modulate fractions of the bit, and those fractions are typically phase shifting the carrier. So the receiver, what will the receiver do then is it will multiply those incoming signals by the same chip signal sequence that was generated at the transmitter to recover the original modulated signal. Usually the systems that are using the DSSS are called code division multiple access. And what we mean by multiple access is that you're applying multiple users to use the same communication channel. So you only have one channel and you have multiple users are using that channel at the same time. And by that way, you're using a wider bandwidth, but you're having more users that can use it. So here, so here in the figure, this is just showing a basic direct sequence circuit. You're going to have here, this is your data here. You're going to have a chipping rate. This is your clock, and you're going to have a chipping rate that is like a fraction of your bit rate here. And you're going to pass it through an XOR gate, and then you're going to binary phase shift key that and send it to through your transmitter. So for example here, if I have my intelligent, this is my original information here. And this is the chipping sequence. So the chipping sequence is something that is random generated, and it's part of your signal. So it's only taking parts of it. Okay, it's chopping it. What you will do here is you're going to do your apply your XOR gate, and we know that for the XOR gate, it's a logic gate where when you have signals different, it's going to give you 1, and if you have them the same, it's going to give you a 0. Okay, and this is the opposite of the XNOR. So the XNOR will always give you 1 when they are the same, but XOR will give you 1 when they are different. So I'm going to notice here, if I have this point here, if I take this point, this is equal to 1, this is equal to 1. Okay, so they are the same. My output here is going to be 0. Now I have 1 and 0. My output here is going to be 1. Then I have here 1 and 1. My output is going to be 0. I have here 0, 1. So these are different. My output is going to be 1, and so on. Now you're going to notice here, so this is going to be like your output here. Okay. Now your modulated phase shift keying, binary phase shift keying is going to work as whenever you have a 1, you're going to have an original carrier that is in phase with the original carrier. And whenever you find a 0, it's going to be 100. This is when it's 0, this is when it's 1. This is going to be 180-degree phase shifted with the original. And then this will be your signal that will be transmitted. So you can see here when they're all like in phase together, that's when you have your 1, and when they are in 180-degree together, that's when they have a 0. So mainly the spread spectrum has a lot of advantages and have been used recently in many applications, and you're going to find this in your quiz for sure about what are the main advantages of your spread spectrum. So as I said, it was first used in the military to detect and prevent any kind of jamming. That is one of the main advantages. Your second advantage is that it will permit many transmitters to operate over the same channel with minimum interference. So there's not going to be, we're using the same channel, the same bandwidth at the same time, and no one's interfering with anybody else because I'm generating random sequence for each user. And it will rarely coincide that the generator is going to randomly do 2 sequences the same. So we can say that it's very minimal error. Also the reduction in fading. So usually we say that when we're transmitting a signal, it will attenuate until it goes to the receiver. The amount of attenuation or fading, it only decreases by 2 to 3 dB compared to any other conventional narrowband systems that will decrease by 20 to 30 dB. Also, it allows the receiver to determine an accurate information about the time the transmitter sent its energy with minimum effect of noise, okay, with minimum effect from the noise. So these are the main advantages of the spread spectrum analysis. We said that we use two techniques, which is the frequency hopping and the direct sequence spread spectrum, and both of them used what we call the pseudo noise code. And the pseudo noise code depends on generating random data. And we said that the main difference here is that in the frequency hopping, I'm generating random frequency, carrier frequency. In the direct sequence spread spectrum, I am creating random pulses to get modulated with my signal. Now, the last thing to talk about in this chapter is the orthogonal frequency division. Let me just sorry for the interruption. So in orthogonal frequency division multiplexing, it's also called a multi-tone modulation. And it's implemented as well today in many wireless applications. Here you're going to find that the data is divided into multiple data streams, and it's transmitted using multiple subcarriers at fixed frequencies over the same wired or wireless communication channels. The main advantage of this technique, it will enable the receiver's demodulators to see only one carrier. And these benefits will include improving the immunity to radio frequency interference. There's not going to be any kind of interference. And it has also a low multipath distortion. So you're not going to find a lot of distortion because every channel is going through a subcarrier that is separate from other demodulators. So I'm going to work out this video here. It's explaining the frequency division multiplexing, the FDMA, and the orthogonal frequency division multiplexing. I see it very useful because it has a lot of animation, so it makes it a little bit clear. And sure, there's going to be some questions in your quiz about those two videos. So let me just work those here. Let's see if I can do it.
Hi, welcome to the 365 Data Science Data Scientist career track. Data scientist is the hottest profession in the world right now.
Hello friends, today, how can we stream a full HD movie seamlessly, which seemed impossible in legacy networks? So friends, in this video we have shown what are the limitations of wireless channel, how wideband single channel are inefficient for transmission. To overcome, how wideband single channel is divided into small subcarriers and increase efficiency by reducing delay spread. How concept of orthogonality is introduced in FDMA and achieves multi-volt throughput. Hi everyone, welcome back to the world of 4G.
Previously we have shown how mobility and global connectivity was achieved by introduction of wireless communication. But there are several complexities associated with wireless channels. Multipath fading. Unlike a wired channel, which uses a fixed path, the signals in a wireless channel can reach a user using multiple paths. All these signals, known as multipath components, may have different channel gain and time delay. This combined effect causes what we know as multipath fading. Delay spread. As a consequence of multipath propagation, the duration of a symbol gets extended. This may interfere with the next symbol. This is called inter-symbol interference or crosstalk. Guard periods are introduced to avoid crosstalk. Frequency selective fading. Signals having bandwidth higher than the coherence bandwidth of the channel faces variable attenuation at different frequencies. This ultimately distorts the signal and giving rise to frequency selective fading. Complex channel equalization techniques are employed to reduce it. Inter-channel interference. Often signal bandwidth of adjacent carrier frequencies overlap with each other, giving rise to inter-channel interference. Guard bands were introduced to avoid inter-channel interference. All these limitations, compounded with the scarcity of bandwidth, gave rise to multiple access technique, OFDMA. Before diving into OFDMA, let us understand multi-carrier wireless transmission system.
Suppose a signal is to be transmitted over a bandwidth B and carrier frequency FC. Then symbol time for this would be TS equal to 1 by B. For a single carrier wideband channel of, let's say, 1 MHz, the symbol time will be 1 microsecond. Given that the delay spread of the channel is of 2 microseconds, the combined symbol time would be 3 microseconds, which means delay spread occupies 66% of the combined symbol time, thus reducing the efficiency of the channel by 1/3. As delay spread is difficult to control, the effect of delay spread can be minimized by using multiple subcarriers of lesser bandwidth. So instead of having a single carrier of 1 MHz, we divide it into 100 subcarriers of 10 kHz, each having a symbol duration of 100 microseconds. So a delay spread of 2 microseconds will have a negligible effect over the channel efficiency. This concept is used in FDMA, which uses slowly modulating subcarriers of higher symbol duration. As these subcarriers are modulated with data, they gain bandwidth centered around the subcarrier's frequencies. Guard bands are used to separate them in frequency domain. We can represent this transmitted signal in the equation form as shown here, where summation of individual symbol multiplied with different carrier frequencies and transmitted at radio frequencies. OFDMA, or orthogonal frequency division multiple access, is a special case of FDMA, where users are provided a set of subcarriers overlapping in frequency domain. However, these subcarriers are specially designed to be orthogonal to each other, which allows them to occupy the same bandwidth without any interference. This in turn negates the use of guard bands. As a result, the subcarriers can be closely packed to increase channel efficiency. Now, before looking at the multiple access part, let's understand how OFDM, or orthogonal frequency division multiplexing, works, and how it's used in long-term evolution.
In OFDM, high-speed data streams of large bandwidth are split into parallel, slower substreams of lower bandwidth called subcarriers. These subcarriers are centered around frequencies in multiples of 15 kHz on both sides of DC. As the lowest subcarrier is of 15 kHz, symbol duration, TS, is equal to 1 by 15 kHz or 66.7 microseconds. Consequently, a 1 subcarrier can provide a symbol rate of 15 ksymbol per second, which is analogous to having a symbol rate of 1 symbol per second for 1 Hz of bandwidth, or half a Nyquist rate. Unlike in GSM or UMTS, LTE supports variable bandwidth as shown in the table. As the bandwidth increases, so does the number of subcarriers in it. Let's take, for example, LTE bandwidth of 20 MHz. which has 1,200 subcarriers and thus subcarrier bandwidth of 18 MHz. 2 MHz used as guard band. Here we have 600 subcarriers on both sides of the DC frequency. All these carrier frequencies are harmonics of 15 kHz, varying from -9 MHz to 9 MHz. In time domain, these subcarriers will be represented as everlasting sinusoids at these carrier frequencies as shown. However, in order to transmit data over these subcarriers, they are loaded with modulation symbols that represent the constellation points of digital modulation schemes, like UPSK and Thoracons. Also, the symbol duration for each of these subcarriers is always equal to 66.7 microseconds, which means that all these subcarriers have a whole number of cycles in one symbol duration. As we know that a rectangular function can be represented in frequency domain as a sinc function which is centered around DC. When multiplying the signal to a carrier frequency in time domain, signal will be shifted in frequency domain by the same amount of carrier frequency.
Thus, we can represent these modulated subcarriers in frequency domain as a series of sync waves centered around the carrier frequencies. Basically, we are having 1,200 such sync waves. There are 2 points to be noted here. Firstly, the subcarriers are overlapping in frequency domain. As we can see, the subcarriers are placed in a manner that all the other subcarriers have a zero component at the peak of one subcarrier. Such subcarriers are called orthogonal. As a result, a mobile can sample the frequency and phase without any interference from neighboring subcarriers. Orthogonality is achieved by ensuring that all the subcarriers have same symbol duration Ts, and the subcarrier spacing is maintained at delta F equal to 1 by Ts. Secondly, presence of negative frequencies. It can be explained by the fact that the subcarriers are transmitted below the radio carrier. So friends, today we learned how information is split into smaller subcarriers in multi-carrier modulation, and how efficiency was increased by placing them orthogonally. In our next video we will show how data starts its journey as a stream of bits and are finally transmitted as radio signal. So friends, don't forget to subscribe to our channel, like our videos and comment your views or suggestions. Happy learning!
Are you tired of the media spinning the truth and pushing false narratives? Well, take a look at this.
So this is the second video. Sorry for the interruption.
Elena, someone.
The form of bits reaches network gateways from various sources. The gateway forwards it to the E node B, but how does the E node B convert them into radio signals and transmit them to the user over the air interface? How does the user equipment communicate back to the node B? Hello friends. Welcome back to the world of 4G. Today we will discuss uplink and downlink data transmission in the network.
As discussed earlier, data is transmitted in OFDMA over parallel subcarriers of 15 kHz. The subcarriers are further divided on the time axis as blocks of one symbol duration, or 66.7 microseconds. This basic unit is known as resource element. Each resource element carries one symbol. Now, in order to transmit data over these resource elements, first data is modulated with specific modulation scheme. This scheme depends on the physical channels mapped on the resource grid. Suppose we have 8 bits of data to be transmitted using UPSK modulation. The data will be divided into 4 parallel streams of 2 bits. Phase and amplitude assignment is done according to the QPSK constellation. Finally, data is placed over the resource elements by adjusting the phase and amplitude of subcarrier to those derived for the data stream. Mathematically, it means multiplying the complex modulation symbol to the corresponding subcarrier frequency. Thus, in a 20 MHz channel, all the 1,200 resource elements carrying 1,200 symbols over 1,200 subcarriers are modulated with appropriate modulation scheme. Now, since the data is modulated over 1,200 subcarriers, a transmitter will require 1,200 oscillators for its generation, and another 1,200 will be required by the receiver for proper demodulation. The hardware complexity and sheer amount of power consumption would have left OFDM to theoretical idea and far from implementation. OFDM was made reality with the advent of digital signal processing techniques. So, instead of using 1,200 oscillators, IFFT solves this problem by converting the parallel frequency domain signals into samples of a composite time domain signal, which are much easier to generate at transmitter side. All we need to do is to send these time domain samples at radio frequencies. As the data is being sampled by IFFT, samples must be taken above the Nyquist rate for faithful reproduction at the receiver. For an LTE spectrum of 20 MHz, the highest frequency component is 9 MHz, which means the sampling rate should be greater than 18 megasamples per second. In other words, 1,200 samples per OFDM symbol of 66.7 microseconds. Since UMTS had a sampling rate of 3.84 megasamples per second, to achieve backwards compatibility, sampling rate in LTE is taken as multiple of 3.84 megasamples per second. Thus, for 20 MHz spectrum, which has a sampling rate of 30.72 megasamples per second, there are 2,048 samples per symbol in OFDMA. The FFT size of the IFFT processor thus depends on the LTE bandwidth as shown.
Now, previously we have shown, in wireless channel due to multipath propagation, we face delay spread and inter-symbol interference. We have also discussed how its effect can be reduced by increasing the symbol duration. Also, how guard period were used to eliminate it. But abrupt changes in time domain during transition period from symbol to guard period causes intercarrier interference in frequency domain and disturbs the orthogonality between subcarriers. So in OFDMA, we employ a more complex kind of guard period called cyclic prefix, in which end part of a symbol is transmitted in the preceding guard period. It also ensures orthogonality between the subcarriers by keeping the OFDM symbol periodic over the extended symbol duration and therefore avoiding intercarrier and interchannel interference simultaneously. Since OFDMA uses composite IFFT samples, cyclic prefix is added by taking some samples from the end of a symbol period and placing them at the beginning.
Now this time sampled signal is converted into analog wave by a digital to analog converter. Further composite waveform is modulated at the desired radio frequency for transmission. For an example, an operator having license for 2,320 MHz to 2,340 MHz. The 18 MHz then will be mapped from 2,321 MHz to 2,339 MHz using analog modulation. And finally, the A-node B transmits signal over air. A-node B informs the user about the allocated subcarriers and the corresponding modulation scheme. So, when the RF signal reaches at the user's terminal, all these processes are reversed, and finally user is able to receive the data intended for it.
Although there are many positives in OFDMA, but IFFT summation of multiple parallel subcarrier results in high peak to average power ratio. High PA/PR results in high power consumption for signal generation. but handheld devices have limited power capacity. This makes OFDMA unfavorable for uplink transmission. In order to overcome this, LTE uses SC-FDMA in uplink direction. In OFDMA, we have one-to-one mapping between symbol and subcarrier, but SC-FDMA allows the symbol to be transmitted in parts over multiple subcarriers. For example, in OFDMA, one symbol occupies one subcarrier of 15 kHz, but in SC-FDMA, same symbol is distributed among multiple subcarriers of 15 kHz. In short, SC-FDMA behaves like a single carrier system with short symbol duration compared to OFDMA. To achieve this, SC-FDMA introduces the endpoint FFT block right after the serial to parallel converter in the OFDMA structure. The FFT block converts parallel sequence of symbols in time domain to different frequency points. Now, peak to average power ratio is proportional to the squared number of carriers involved. SC-FDMA reduces PAPR by reducing the number of carriers. Obviously, there are problems in single carrier transmission as we discussed earlier, but the side effects are reduced by ensuring that the total bandwidth over which a symbol is transmitted is still not too high. Apart from this, remaining block in the uplink direction is same as used in downlink direction.
In our next video, we will be talking about physical transport in
So we are done with this one. This is chapter. This is the end of the chapter. Please review your slides along with the video before you try to attempt your quiz. Thank you.